people have done recursion unintentionally during the course of the year. Recursion is simply where a method calls itself, by the way, right? And so, and it has its uses. It can make, it technically never have to be recursion. Anything that can be done in recursion can be done without recursion. But it can make some code much more elegant, okay? It's very hard to do without recursion. Yes, sir? It is where a method calls itself. That's it. So our method's called fun, and it's calling itself. Now, it's essentially a form of looping, by the way. And one logical error when you're making a loop is to have a loop that runs forever, that can never stop. And that can happen here. Label this right here, the if. Let's call that the stopping condition. You kind of need that. So like I said, I would label that. Another name for that is the base case. When doing recursion, you must have a base case to prevent infinite recursion. And I'll tell you, with like a while loop, you can do this, by the way. If you said while true, you'd have a loop that never stops. But that's all that would happen. Your loop would just go on forever. Here, when you get in for recursion, your program runs out of memory. Now let me explain why. We said this method is going to call itself, and so that makes it recursive. But every time you do a method call, imagine this: you make a program, you have a main method. Main method calls the print line method, and the print line method is going to call the square root method. Like you want to print the square root of 25. Well, think about this: your main method is calling another method, so your main method stops what it's doing. That method call gets put on the stack. There's a stack in the computer that keeps track of all your method calls, and it calls the printline method. But the printline method can't do its job until it knows what to print, right? So the printline method stops what it's doing. And by the way, we never actually look at the code, but somehow the printline method gets what you want on the screen onto the screen. It has to be involved with the hardware somehow, right? And so the printline method has a job to do, but it can't do it. So it's when does this work? That method call goes in the stack. And then the first method, if it isn't calling any other methods, it just does its job, does all the math involved in calculating the square root, and returns back with the answer, which now the printline method can carry on this work, right? And so the printline method gets pulled off the stack, it finishes the job, the main method can carry on with whatever it's going to do after that. That's how method calls always work, I'm saying. We haven't talked about the stack before because they don't really need it. But that's what's going to happen here as well. But not because they're recursive, that's just how method calls work. Now, if you look at the worksheet, 1 and 2 are different from 3 and 4. And that's the two basic kinds we'll talk about. This one, it's a bunch of print methods. And so, whereas the bottom ones are more math-based. I'm sure they work differently. So first of all, and I'm going to abbreviate everything. We're calling the fun method. I'm just going to call it F3, fun3, okay? So what does this method do with an input of 3? Well, it prints 3. So just put, I'm going to call it P3 because it says it's going to print 3. We're just listing what the method will do for this input. And then it's going to call the fun method with an input of 2, right? If X is 3, that's a 2. Just write that down. Okay? So once again, that's what our method's going to do. And it's going to do those things in this order. So first of all, when we run the print method, we're going to see a 3. So wherever you're putting your output, go ahead and put the 3 there. Okay? Now, so we printed the 3. Now we call fun of 2. Well, that's a new method call. So let's draw that here. So we're calling our fun method. We're starting over with x being 2. And it was working on f of 3. It suspends working that. And one thing it keeps track of with these method calls, this variable is a local variable. It's a parameter, but I'm saying when it puts f of 3 on the stack, it keeps track of the value of x, which is 3. And it's starting over with fun, a new version of fun, with an input of 2. If you start this method with 2, what's it going to do? Well, print 2, and then called fun with an input of 1. That's 2 minus 1 is 1, isn't it? So go ahead and run the print method. We're just going to run this code. Run the print method, so you see the 2. And now we call f of 1, which we need to write down what that does. What is f of 1 going to do? First of all, it's still greater than or equal to 1, so it does this code again, which means it prints 1, and then calls f of 0. So, and we call f of 0. And what does f of 0 do? Nothing. F0 does nothing at all because it doesn't do that, if nothing else. So you can just leave it blank. You want to put an X just to, as a little symbol that it does nothing. You can, but just, there's nothing to put there because it does nothing. Which means now we can return back. Now, what we're doing here, you might write this down, it's called tail recursion. Tail recursion is where the recursive call is at the end of the code. And so it's kind of boring, frankly. Since this is the first method that technically finished. And so when it's done, you return back here, right after the method call, but that was at the end, wasn't it? There's nothing more to do. And then now that F1 is technically done finally, you can return back to where F1 is called. F2 called F1, didn't it? So when F1 is done, you return back here, and now F2 is done. And so you can return back to where F2 is called. And so that's what's really happening, but there's nothing else to be done, so it's kind of boring, like I said. Let's do number 2 now. Except I want to change this, switch these two, and so like move the print statement after, because I don't want to do another tail recursion. Okay? So change your code. Is that how it is in your paper? Or is yours need to be changed? Okay. I need to change it for next year. Alright, let's go do the same thing. It's going to look different now, but we'll, well, it did sort of look very similar. So we call F3. If X is 3, we're going to call, first run this line, this statement, and then the next one. So we're going to first do F of 2, and then we'll print the 3. Is that okay? Once again, for right now, X is 3, and so that's a 2 and that's a 3. Now, once again, it cannot do F of 3. I mean, it can't carry on until it does this method call. So we need to show what F of 2 does. So if you start over and X is now 2, what does F of 2 do? It calls F of 1, and then calls the print line method, or the print method with an input of 2, because X is 2 right now. So that's what it's going to do, but once again, it can't, it has to, you're calling F of 1 first, obviously, so you suspend work there until you finish F of 1. So we start over again. And by the way, keep your eye on the ball. I'm saying the recursion keeps going until X gets below 1, right? So, all right. So what is that? What do I put for F of 1? What does it do? F of 0, and then we'll print the 1. So let's see what F of 0 does. What does F of 0 do? It prints 0, doesn't it? So let me write that down. So this is the first time we're actually going to see something printed, right? And so here, somewhere where you're supposed to put your output, put a 0 there. And now we go back. So F of 0 had one job to do, print 0. It did that. So since it's done, you return back and get the arrow right. You return back to where F of 0 was called. So right after F of 0, what happens next? You print the 1. Which means now F of 1 is done with this job. So you can go back to where F of 1 is called from, which was F of 2. F of 2 called F of 1, right? Now that F of 2 is done with its first step, it can do the second step, which is to print the 2. And then finally, now that F of 2 is done, you can turn back to F of 3, and F of 3 can finish this job. And so you see the 3. And that effect was to print it in reverse order of last time. Also, this time it printed a 0. Last time it didn't. Why? Because last time it just did nothing when X is 0, and this time it printed the 0, right? Let's go to this. Yes?
If you didn't change it, would have been 0, 1, 0.
Exactly. If I kept this in the order it was, if I kept it as tail recursion, it would have been 3, 2, 1, 0. And so, think about this. Once again, it's just looping, really. It's obviously a different kind of looping. And we'll get into where it's useful beyond just little simple stuff like this. One thing is just mazes. You want to solve a maze, recursive algorithm is really easy to write. It'd be pretty hard to do it the other way. I don't know how to do it other than recursive. I don't want to know. Now, let's do number 3. Totally different kind of situation now, because once again, this is more math-based, okay? And so, like I said, I showed the work differently. There's no print statements here, right? So, what I would do is, first of all, if x is 3, you're not doing this, you're doing this, obviously. So if x is 3, that's a 3. And then you have to call the method again with x being 2, yes? So I'm saying, if x is 3, this is what I had there. Now, listen, this is not that hard, really. It's as if, like, if you had something that's supposed to return 3 plus the square root of 25, what would happen? It would go call the square root of 25, come back with 5.0, and then do the addition, yes? Same thing here. You have to spend work on this, technically put this method call in the stack, and figure out what f of 2 is. So I will show it this way. F of 2, well, you start over. 2 is not less than 1, so you do the same thing. It's 2 plus f of 1. Well, once again, it can't add this until it figures out f of 1. So f of 1 is 1 plus f of 0, which it needs to figure out f of 0 now. F of 0 now is just 0, right? So that ends the recursion. So I would just write it this way, f of 0 is 0, which means now you can come back, return. F of 1 was waiting to figure out what that was. Now that you notice 0, you can compute that sum, which is 1, obviously. Now that you know what this is, you can compute that sum, which is 3, I think. 2 plus 1 is 3. And now that you know that sum, you can finish the job, and the answer is 6. Questions?
What order do you return it? So
No, and that's a good question. Look, what did we call? We called fun of 3, which returns the answer 6. Okay? And so there's only one answer. That's it, and I'm glad you said that. I forgot to emphasize that last period. The output here is 6. To get there, this method, called f of 2, which called f of 1, which called f of 0, which returned values, but all went in calculation of that sum. So yeah, the output's going to look totally different too. All right, try number 4. All right, do number 4 now. So look, we're supposed to figure out what the result of f of 3 comma 6 is. And once again, so x starts out as 3, y starts out as 6. Y is not 2 yet, so we're going to run this code, obviously. And all that's changing is y, by the way. X is going to stay 3 the whole time. So you run this code, which means you have to figure out f of 3 comma 5 and plus 3. And so once again, before you can do this, you have to start over and figure out f of 3 comma 5, which you run the same code. So you do find f of 3 comma 4 plus x, which is 3. And then you have to figure out f of 3 comma 4, and it just, once again, you get all these different method calls you have to figure out. Until finally y is 2, and since y is 2, you're running the other part, the base case, which returns the value of x, which is not 2, it's the 3 actually, right? So that's what stopped the recursion. And then once again, it's like, by the way, the movie Inception. Very similar, they go down in these different levels of frames, they have to come back up through those in the same or the opposite order, right? And no, Inception. And so it calls f of 2, which is 3, so you come back, and now that you know this is 3, you get 3 plus 3 is 6. And since you know that answer is 6, plus 3 equals 9. Since that answer is 9, plus 3 is 12, and you work your way back to the final answer. And once again, on the blank, the answer blank, you put just 15. That is the answer. That is what gets returned by this. There's no print line, so you don't see every individual answer printed, obviously. Okay? Try the next one now. How many steps of recursion were on the last one? None, right? I mean, y starts out as 2, so the answer is just 4. because it's tail recursion if the recursion call is at the end. So like number two, originally was tail recursion, then we changed it so it wasn't.